Hello friends, so today we are going to solve questions from modern physics, and these questions are from the year 2021. Total we are going to solve 17 questions, and all these questions are from the mains part only. So first question: in the given figure, the energy level of hydrogen atom have been shown along with some transition marked A, B, C, D and E. The transitions A, B, C respectively represent. So we are given that transition are given as A, B, C, D and E, and various levels are given to us. So levels start from N1 and maximum it goes to N5. Okay, sorry, maximum up to will go to infinity. Okay, and before infinity the highest one is our N is equal to 5. So we are going to start with transition A. So we have transition A. Transition A, it starts from N infinity and to N is equal to 1. Okay. So this you can say is a representation of Lyman series, or it can be further subcategorized as series limit of Lyman series. So this can be called as series limit of Lyman series. Next transition is for our B. So we have our transition B, and transition B starts from N5 and it ends at N is equal to 2. And this is, you can say, transition represents a Balmer series, and in terms of series you can say line, we can call this as a third line of Balmer series. So we call this as third line of Balmer series. Then we are having transition C, that is from N5 to N3. Transition C, and it is from N5 to N3, and this we can call as Paschen series, or specifically we can call this as a second line of Paschen series. So therefore option number 3 is correct. Next question. It states that the de-Broglie wavelength of a proton and alpha particle are equal. The ratio of their velocities is. So we are going to start with de-Broglie wavelength, and then from there we are going to solve with respect to their velocities. And we know the relationship that our de-Broglie wavelength that is lambda is equal to h upon momentum, or we can say h upon mass into velocity. So we have two de-Broglie wavelength. One is for proton, so we can say for proton we can write this as lambda p is equal to h upon mass of proton, velocity of proton. And next is our alpha particle, and for alpha particle we can write this as lambda alpha is equal to h upon mass of alpha and velocity of alpha. And we are given that both wavelengths are equal, so we are given lambda p is equal to lambda alpha. From here we can write that h upon mass of proton, velocity of proton is equal to h upon mass of alpha, velocity of alpha, where h and h cancels out, and this gives us that a mass of proton, velocity of proton is equal to mass of alpha and velocity of alpha. We have to find out the respective ratio of their velocities. Therefore we can write that our velocity of proton divided by velocity of alpha will be equal to mass of alpha and mass of proton. And we know that our mass of alpha is 4 times mass of proton. So we can write this as 4 times mass of proton divided by mass of proton. So this proton mass cancels out, and this comes as 4:1. So the ratio is our 4:1. Next question. It states that an alpha particle and a proton are accelerated from rest by a potential difference of 200 volt. After this, their de-Broglie wavelengths are lambda p and lambda alpha respectively. The ratio of lambda p to lambda alpha is. So the two particles are accelerated by a potential difference of 200 volt. It means this potential difference is going to provide energy or kinetic energy to our both the particles. Okay. So we can write that energy gained by each particle and let us suppose that is our kinetic energy, which will be equal to charge multiplied by the potential difference. And we are having two particles. First particle is our alpha particle, and so alpha particle we can say the charge will be equal to plus 2 times the charge in electron, and other one is our proton. So we can say this will be equal to our charge, let us call this as alpha, and this for proton this will equal to plus E. And kinetic energy we can write in the form of the our velocity also. So we can say that our kinetic energy is equal to half m v square, which is equal to q multiplied by v. Therefore our velocity will be equal to 2qv divided by mass m and its square root. Now we can divide, or rather we can say, let's use de-Broglie wavelength equation. So we can say de-Broglie wavelength that's of lambda is equal to h upon mass into velocity. Here we substitute our velocity. So we get lambda is equal to h upon mass square root of 2qv divided by mass. So this can be written as h upon square root of 2mqv. And we are having two particles, two wavelength. So therefore from here we can write that for our proton we are going to get this h upon 2 mass of proton, charge on proton, and potential difference is same. And similarly we can write it for our alpha particle also. So this comes h upon 2 mass of alpha, charge of alpha, and potential difference, that is our v. And we have to find out the ratio. Therefore we can say that our ratio, that is our lambda p upon lambda alpha, will be equal to, we have this as h upon 2 mass of proton, charge, potential difference, and this comes as h upon 2 mass of alpha, charge on alpha, and potential difference. Here this h2 potential difference cancels out, and this will be equal to our square root of mass of proton, charge of proton, and square root of mass of alpha and charge on alpha. Now we can just substitute. So we get this as our alpha lambda p upon lambda alpha is equal to, let's make this square root common, mass of alpha is our 4 times mass of proton. So we can write this as 4 times mass of proton, and charge on alpha is our plus 2e. So this is mass of proton and this is plus e. So here this mass of proton, mass, and E cancels out, and this comes as square root of 8, and approximately this is our 2.82. So option number 4 is correct. Four is correct. Next question. It states that the wavelength of a photon emitted by a hydrogen atom when an electron makes a transition from second to first state is. So in this case we have transition from second to 1, and we have to find out the wavelength. So first of all we are going to find out the energy difference between the two levels, and then we can use our standard relationship between wavelength as well as energy. So we can say energy difference between the level, energy difference between levels, and for that we are going to use the formula, that is E of n is equal to minus 13.6 upon n square. So we can say our energy difference delta E is equal to our E1 minus E2, and we can take this our 13.1 upon 1 square minus 13.6 upon this is our 2 square. So this energy difference will be coming as minus 10.2 electron volt, but we are only interested in the magnitude. So we can say our delta E in terms of magnitude is equal to 10.2 electron volt. Now we can use the wavelength formula. So we know that our energy E is equal to hc upon lambda. So from here we can say our lambda is equal to hc upon E. E here we can just replace it by delta E difference. So this comes as our, and Hc in terms of our electron volt is 1240 and delta E is our 10.2, and in this case whenever we substitute Hc as 1240 electron volt, the unit of this wavelength is automatically our nanometer, and this gives us that our lambda will be equal to 1 to 1.6 nanometers. So option number 4 is correct. Is correct. Next question. It states that the stopping potential for electrons emitted from a photosensitive surface illuminated by light of wavelength 491 nanometer is 0.710 volt. When the incident wavelength is changed to a new value, the stopping potential is 1.43 volt. The new wavelength is. So we have two wavelengths, one is known and another we are going to find out, and their respective stopping potential is given to us. So let us say that initial wavelength is our lambda 1, which is given as 491 nanometer, and then we are having stopping potential also. So we can say initial stopping potential V1, that is our 0.710 volts, and we are having new stopping potential that is our V2, which is our 1.43 volt, and for this stopping potential we can write our new wavelength, that is our lambda 2, which we are going to find out, and we are going to make use of photoelectric equation and try to solve it. So we can say photoelectric equation, which tells that the kinetic energy max is equal to our, we can write this kinetic energy max in terms of EVS is equal to Hc upon lambda minus phi. Here this Vs is the representing our stopping potential. Okay. So for this particular equation, we can write our Vs is our stopping potential, and we have two value of stopping potential and two value of wavelength. Therefore we can say that our E times V1 is equal to Hc upon lambda 1 minus work function, and second one is EV2 is equal to Hc upon lambda 2 minus work function, and we can just subtract these two equations. Subtracting, we get E V2 minus V1 will be equal to Hc, we can take as common, this comes as 1 upon lambda 2 minus 1 upon lambda 1, and we substitute the values. We get this as V2 is our 1.43 minus 0.71, and Hc is our 1240 electron volt, and this upon 1 upon lambda 2 we are supposed to find out, and this becomes 1 upon 491. And on the left side we are going to get this as 0.72 and divided by 1240 will be equal to 1 upon lambda 2 minus 1 upon 491. This can be written as 1 upon lambda 2 is equal to this will be giving us 581 into 10 raised to power minus 4 plus 1 upon 491. So from here we get that the value of lambda 2 will be approximately equal to 382 nanometers. So option 3 is correct. Next question. It states that an electron of mass Me and a proton of mass Mp equal to 1836 times mass of electron is moving with the same speed. The ratio of their de Broglie wavelength, lambda electron to lambda proton, will be. So this is directly based on the de Broglie wavelength formula. So we can say that our de Broglie wavelength, which is our lambda, is equal to h upon mass velocity, and we are having proton and electron. Therefore we can write that lambda E is equal to h upon mass of electron, velocity of electron, and lambda proton will be equal to h upon mass of proton and velocity of proton. And we are interested in the ratio, therefore we can say ratio is our wavelength for electron and wavelength of proton is equal to h upon mass of electron, velocity of electron, and h upon mass of proton and velocity of proton. Here this h and h cancels out, and this we get as mass of proton, and okay, and we are also given that velocity of electron is equal to velocity of proton. This is also given to us, so these two velocity terms also cancel out. So we get this as mass of proton divided by mass of electron. Therefore we can write that lambda E upon lambda P is equal to mass of proton is given as 1836 mass of electron, and this is a mass of electron cancels out, so the ratio comes as 1836. So ratio will be our 1836. Next question. It states that if lambda 1 and lambda 2 are the wavelengths of the third member of Lyman and first member of Paschen series respectively, then the value of lambda 1 is lambda 2. It means the ratio of lambda 1 and lambda 2 is. So we can use directly the Rydberg formula. So we can say that Rydberg formula, which gives 1 upon lambda is equal to R 1 upon nf square minus 1 upon ni square, where nf is a lower energy level and ni is our higher energy level. Here our nf is our lower energy level and we have to remember this lower energy level is fixed for each series. Fixed for each series, and Ni is our high energy level and which varies for you can say series to series. So this varies series to series, or sometimes it is called with member number also, series to series. Let me call it as a varies with member number. So first is our Lyman series. So we can write that for Lyman series, and for this our lower energy level, that is our NF, it is fixed at 1, and the higher energy level for Lyman series it says that the third member of. Okay. So therefore let me write it for third member. So here our Ni will be equal to 4, and next is our for first member of Paschen series. So you can say for first Paschen series, our NF is equal to 3 and our Ni, that is the first member, is equal to 4. So we can divide our Rydberg formula according to the wavelength also. So for Lyman the wavelength is given lambda 1, and for Paschen the wavelength is given as lambda 2. Therefore we can write that our 1 upon lambda 1 is equal to our R, and we have this as 1 upon 1 square minus 1 upon 4 square. This will be coming as 15 R upon 16, and we are having 1 upon lambda 2 is equal to our R, and this comes as 1 upon 3 square minus 1 upon 4 square. This comes as 7 upon 144 times R, and from the first we can say our lambda 1 will be equal to 16 upon 15 times R, and from here we can say our lambda 2 is equal to 144 divided by 7 R. Now we can find out the ratio. We are having lambda 1 upon lambda 2, which will be equal to 16 upon 15 R divided by 144 divided by 7 R. R and R cancel out, and this can be written as 16 upon 15 multiplied by 144, and 7 goes here, and this ratio will be coming as 7 upon 135. So option 3 is correct. Is correct. Next question. It is asked that the recoil speed of hydrogen atom after it emits a photon going from fifth state to first state will be. So in this case, first of all we are going to find out energy, and then we are going to use the conservation momentum to find out the recoil speed. So let's first of all find out the energy emitted by the photon. So you can say energy of emitted photon energy of emitted photon, and that will be obviously the difference between the energy of our two states. And for that we are going to use the formula that E of n is equal to minus 13.6 upon n square electron volt. So the energy emitted, let us suppose that is our E, will be equal to our difference between two levels. So we can say 13.6, and we have this as 1 square and 1 upon 5 square, and this energy is approximately equal to 13.056 electron volt, and we are going to convert this energy into joules. Therefore we can say our energy E is equal to 13.056 multiplied by 1.6 into 10 to the power minus 19, which gives us 2.08 into 10 to the power minus 18 joules. Now we can use the momentum and energy relationship. So we can say the momentum of emitted photon that is our P is equal to energy upon the speed of light, which is our C, and therefore we can say our momentum P is equal to energy is our 2.08 into 10 to the power minus 18, and C is into 3 raised to the power 10 to the power 8. So we get momentum will be equal to 6.9 into 10 to the power minus 27. So now the conservation of momentum the momentum of photon will be equal to the momentum of recoil of hydrogen atom. So we can write that recoil momentum of hydrogen atom will be equal to momentum of emitted photon, or we can say photon momentum. And so recoil momentum will be our mass of our hydrogen. Suppose recoil velocity is our VR, will be momentum photon is our P. So we can say our recoil velocity will be equal to P upon mass of our hydrogen. Recoil is our 6.9 into 10 to the power minus 27, and mass is our 6.9, yeah, 1.6 into 10 to the power minus 27. So 27 cancels out. Therefore, we get our recoil velocity VR will be equal to 4.17 meter per second. So option 1 is correct. Next question. It states that two streams of photon possessing energy equal to twice and 10 times of work function of metal are incident on the metal surface successively. The value of ratio of maximum velocities of photoelectrons emitted in the two respective cases is x is to y. The value of x is. So in this case, we are given two streams of photon and their energy is equal to twice and 10 times the work function. And we are supposed to find out the ratio of their respective maximum energies. So we can write that photon energies so we have two photons. Let us suppose first energy is E1, which is our 2 times work function. Second energy is our E2, which is 10 times the work function. And the velocities, let us suppose, is our V1 and V2. So the ratio V1 is to V2 in this question is specifically given as x is to y. So we are going to use directly our photoelectric equation. Photoelectric equation, which gives us the kinetic energy maximum, will be equal to energy of the photon minus the work function, and that will also equal to our half m v square. So we can write that our kinetic energy for first will be equal to our E1 minus work function, and E1 is our 2 phi, so this comes as 2 phi minus phi, which is equal to phi, and this will be equal to our half m v1 square. Second, we can write the kinetic energy second is equal to our E2 minus work function, that is our 10 minus phi will be giving us 9 phi. This will be equal to half m v2 square. Now we are going to take their ratio. So we can say ratio, we have our half m v1 square, half m v2 square is equal to phi upon 9 phi. Here this half m and phi cancels out, and this comes as 1 upon 9, which gives us that our v1 upon v2 is equal to 1 upon 3. But in the question we are given that this v1 upon v2 is equal to x upon y, which is equal to 1 upon 3. So from here we can say value of x is equal to 1. Next question. It states that according to Bohr model, in which of the following transition will the frequency be maximum? So we have to find out the value of the n, or we can say starting and initial value and end value of n for which frequency will be maximum. And we know that our, you can say, frequency of emitted photon is proportional to our difference in energy. Okay. So we can write that our frequency of emitted photon is proportional to energy difference. Or we can write that frequency f will be proportional to energy difference, and this energy difference will be our initial energy minus final energy, or we can say this will be equal to 13.6, and we have 1 upon our nf square minus 1 upon ni square. So for all these 4 options we are going to find out our delta E, and for which the maximum value of delta E will be resulting in maximum value of the frequency. Therefore we have option number 1, which gives us that value of n to value of n is equal to 3. So this gives us that our delta E is equal to 13.6 upon 1 upon 3 square minus 1 upon 4 square. So this will be equal to approximately 0.66 electron volt. We have option 2, and this gives us n2 to n1. Therefore our delta E is equal to 13.6, and we are having this as 1 upon 1 square minus 1 upon 2 square, which gives us approximately equal to 10.2 electron volt. We have our option 3, which gives us n5 to n4. Therefore delta E is equal to 13.6, and we have this as 4 square minus 5 square, which is approximately equal to 0.31 electron volt. And finally we have our n3 to n2, which gives us that our delta E is 13.6, and we have this as 1 upon 2 square minus 1 upon 3 square, approximately equal to 1.89 electron volt. Therefore the maximum value is our 10.2. Okay, so this will be giving us maximum frequency, that is transition from n2 to n1. Therefore option number 2 is correct. Next question. It states that an X-ray tube is operated at 1.24 million volts. The shortest wavelength of the produced photon will be. So this is directly based on the law, which is also called as a Dion-Hunt law. So we can say this is our Dion-Hunt law, and which gives us that the minimum value of the wavelength will be equal to our Hc and divided by EV. And we know that standard value of Hc, we substitute the values directly. This will be giving us lambda minimum. Hc in electron volt is 1240, and we have this as 1 to 4 million volts. So this comes as 1 to 4 into 10 raised to power 6, and this automatically wavelength will be in nanometer. So this gives us, it will be equal to 1 into 10 raised to power minus 3 nanometers. So option number 1 is correct. Next question. It states that two radioactive substances X and Y original have N1 and N2 nuclei respectively. Half-life of X is half of half-life of Y. After 3 half-lives of Y, number of nuclei of both are equal. The ratio of N1 and N2 is. So this is directly based on our, you can say, decay law, and we can write that our N of T is equal to our N naught 1 by 2, and this comes as raised to power T upon T half. We have two substances X and Y, so let us assume that our half-life of Y is our Ty. So from here we can say that half-life of X will be equal to half of a half-life of T, that is our 1 by 2 multiplied by half-life of Y. And we are supposed to find out after 3 half-lives of Ty. Therefore we can say that after T is equal to 3 half-life of Ty, we can find out our Ny, and we can say that our Ny will be equal to our Y is our second one, which is of N2, because initial is our N naught in general formula, but specifically here it is given as N2, and this comes as our 1 by 2, and this will be our 3 Ty, and its half-life is Ty. So Ty cancels out, so we get this will be equal to our 1 by 8 times N2. And for our X, this was for Y. So we can say for X, number of half-life elapsed, number of half-lives elapsed will be equal to T upon its T half. We substitute respectively, we get this as our T is our 3 times Ty, and Tx is our half of Ty. Here Ty and Ty cancel out, so we get the value of T will be equal to 6. So now easily we can find out our N of X. Therefore we can say our Nx is equal to, initial it is called as N1 by 2, and this is our 1 second, sorry, this is not T, okay, let me, this is our T upon Tx. which we found at 6. So from here we get our n1 1/2 n raised to power 6, which will be equal to 1/64 times n1. And it states that after this time both are equal. It means ny is equal to nx. So we can say that our nx is equal to ny, and this is a given to us. We simply substitute their respective parts. Nx is our n1/64. This is n2/8. Therefore, we have the ratio that n1/n2 is equal to 64/8, which gives us 8:1, or 8/1. Option 3 is correct. 8/1. So option 3 is correct. Next question. It states that the wavelength of an X-ray beam is 10 angstrom. The mass of fictitious particle having the same energy as that of X-ray photon is xh/3. The value of x is. And so here we are going to start with the energy of photon, and then this we can easily relate with our equivalent mass concept. Therefore, we can say photon energy that is our E is equal to hc/λ, and we simply substitute the values. We get our energy E is equal to h is our 6.6 into 10 raised to power minus 34, C is our 3 into 10 raised to power 8, and wavelength is our 10 angstrom 10 raised to power minus 9, 10 raised to power minus 10. And this approximately equal to 1.9 into 10 raised to power minus 16 joules. Now we can use the equivalent mass with the same energy, because it says that they are having the mass of fictitious particle having the same energy as that of X-ray. Therefore, we can say equivalent mass of a particle with same energy we can write that our E is equal to mc square, and from here we can find out our mass. So we can say our mass is equal to E/c square. So this will be coming as 1.9 into 10 raised to power minus 16 and 3 into 10 raised to power 8 whole square, approximately equal to 2.2 into 10 raised to power minus 33 kg. Now this mass is said to be xh/3. So we can equate them. We can say the given formula for mass is our xh/3, which will be equal to 2.2 into 10 raised to power minus 33. And we are supposed to find out the value of x. So from here we can say that our x will be equal to 3 into 2.2 into 10 to the power minus 33 and divided by h is 6.6 into 10 to the power minus 34. Therefore, we can say that our value of x is approximately equal to 10. Value of x is 10. Next question. It states that a radioactive sample is undergoing alpha decay. At a time t1, its activity is A, and another time t2, the activity is A by 5. What is the average lifetime of the sample? So we are having two times t1 and t2 and their respective activity is given to us. So we can use radioactive decay law in terms of activity. Radioactive decay law, and we can write that A of t will be equal to A naught e raised to power minus lambda t, and we are having two different times and their respective activities. Therefore we can say at t is equal to t1, our activity is A, and one second, yeah, so this activity A by 5 and A e raised to power, one second, oh, my mistake, I've written it. We are given that there is the change in activity from A to A5 when time changes from T1 to T2. Okay. Therefore, we can write that the activity changes from A to A5 in time T1 to T2. Therefore, we can write now it as A upon 5 is equal to A e raised to power minus lambda, and this we are having T2 minus T1, and this A and A cancels out, so we get that our e raised to power minus lambda T2 minus T1 is equal to 1 upon 5. So we can take, or in simpler terms, we can write this will be equal to our minus natural log of 5 is equal to our minus lambda T2 minus T1. Here minus and minus cancels out, and we need to find out our average lifetime. Okay, so we need to lambda. Therefore, we can say our lambda will be equal to natural log of 5 T2 minus T1, and we know that our average lifetime will be equal to tau 1 upon lambda, and this comes as our natural log of 5 T2 minus T1. So T2 minus T1 natural log of 5, option 3 is correct. Next question. it states that an EM wave of frequency 5 GHz is traveling in a medium whose relative electric permittivity and relative magnetic permeability both are 2. Its velocity in this medium is. Okay. So we are given that frequency is given to us, that the frequency is our 5 into 10 to the power 9 Hertz, and we are given relative permeability. So we have epsilon r will be equal to 2, and we have mu of r is also equal to 2. So we know that the velocity of our EM wave in a medium velocity of EM wave in a medium, that is our v, will be equal to c upon square root product of mu r and epsilon r. We are going to simply substitute their values. So we get our velocity v is equal to 3 into 10 to the power 8 and square root of this comes as 2 multiplied by 2, which can be written as velocity will be equal to 1.5 into 10 to the power 8, and we are given that this value is 10 to the power 8. So we get this as 1.5. Sorry, not 1.5, but here it is 10 to the power 7, my mistake. So this is 10 to the power 7, so this comes as 15. Next question. It states that an EM wave of frequency 3 GHz enters a dielectric medium of relative electric permittivity 2.25 from vacuum. The wavelength of this wave in that medium will be. Okay. So here once again we are given as frequency, which is 3 GHz, so 3 into 10 to the power 9 Hertz, and relative electric permittivity is given to us, that is our epsilon r is our 2.25, and it enters a dielectric medium, so we can say it is non-magnetic, so mu of r will be equal to 1, and it is incident from vacuum. So we have to remember this is incident from vacuum. Therefore, we can use the formula that the velocity in the medium will be equal to speed of light and square root of mu r and epsilon r. So this comes as 3 into 10 to the power 8, mu r is our 1 into 2.25. So this gives us velocity will be equal to 2 into 10 to the power 8 meter per second. Now we can easily find out the wavelength. Lambda is equal to v upon frequency. So this is 2 into 10 to the power 8 and frequency is our 3 into 10 to the power 9 will be equal to this can be written as 0.066 meters, but the option that is given as 10 to the power minus 2. So this is our into 10 to the power minus 2, and it is in centimeters. Okay, so this is in centimeters. So we can write that this will be equal to 6.66 centimeters, and with respect to this 10 to the power minus 2, this will be coming as 666. So the answer will be 666 10 to the power minus 2. Next question. It states that a radiation is emitted by 100,000 watt bulb, and it generates an electric field and magnetic field at P, placed at a distance of 2 meters. The efficiency of the bulb is 1.25%. The value of peak electric field at P is x into 10 to the power minus 1 volt per meter. The value of x is. So we are given power of the bulb. So we can say that power of the bulb that is given to us as 1000 watts, and we are given efficiency that is 1.25%, or we can say this will be equal to 0.0125, and distance let us suppose that is our R is given to us as 2 meters. We have to find out our E naught, peak electric field. So first of all, we are going to find out the radiated power. So you can say our power radiated, let us call this as P radiated, P rad, which will be equal to our efficiency multiplied by our this power of the bulb. Therefore, we get that this P radiated efficiency is 0.0125 multiplied by 1000. This comes as 12.5 watts. Now intensity at 2 meters. Intensity at R is equal to 2 meter. So we can say that the radiation is basically isotropic. So we can write the formula. So we can say radiation is isotropic. Therefore, intensity, that is our I, will be equal to P radiated divided by our 4 pi r square. I'll simply substitute the values now. So we get our intensity is equal to P radiated is 12.5, and this comes as our 4 pi, and we have r square, that is our 2 square, giving us intensity is approximately equal to 0.248 watt per meter square. Okay, and we are supposed to find out the peak electric field. Okay, and we can say that for EM wave, we know that our intensity is equal to half C epsilon naught and E naught and its square. Therefore, our E naught will be equal to twice I, and this comes as C epsilon naught and its square root. We simply substitute the values. This will be equal to 2 times 0 248, C is 3 into 10 to the power 8, epsilon naught is our 8.8 into 10 to the power minus 12 and its square root. So this E naught will be approximately equal to 13.6 volt per meter. So we get that our E naught is equal to 13.66 volt per meter, but given it is given as 10 to the power minus 1 and it is x. So we can say that value of x will be equal to 136.6 or approximately 137. So value of x is 137. So this completes all the questions from the year 2021, a total of 17 questions. Thank you.